Today, I'm going to talk about decoder architecture in transformer model. As I mentioned before, transformer model has decoder and encoder. In the previous classes, I was talking about encoder architectures. The most unique engineering and principles applied to encoder in transformer model is self-attention. So I was talking about the basic principles of self-attention for last two classes. Self-attention is a matrix form to make a connection between words, who is important and what is the strength of relationship between wordings. And now I would like to talk about the decoder architecture. This is overview of the architecture. You have input sequence x1, x2 to xt. For example, I am a boy or I am studying at KAIST. This sequence T could be 1,000 or 2,000 or million, depending on applications. If you want to give an input to the encoder of whole textbook, T sequence number could be 10,000 or million numbers. Of course, if you want to handle those long sequences, you may need large supercomputers in parallel computing. GPU may have computational core maybe range 10,000 or 20,000 or 30,000. But in this range of long sequences, we may need a new GPU that may have millions of number of cores. And they have to do the matrix calculations in parallel. As well, in addition, memory has to have interconnection path between GPU and memory DRAM, where the number of interconnections should be more likely millions number. And this input sequence will be converted to a vector form that is called as word embedding. Usually I know that it is 520-bit size. If you want to add more properties of wording, like Korean, English, Japanese, or physics, science, we may have many different types of languages. If you want to extend more or more languages and properties, this bit sequence to describe word embedding may increase. But of course, if you increase this D number 512, you need more and more size of GPU and memory and supercomputing. In addition to that, we have positional encoding. Our language has different meaning depending on the position of each word. So word position is very important to deliver a meaning. So because of that, position is also encoded. In the later part of our class, I'm going to talk about how are we going to add positional encoding to the word embedding. So this initial process is a kind of preparation process before the encoding in transformer model. So embedding and the positional encoding, there might be many different ways. But depending on that is the secrecy of each company. We may have different performances. For example, depending on the word embedding and positional encoding method of Korean language, each large language model using transform model may have different performance. Some of the model may be good in Korean, some of them may not be good. This is going to be input to the encoder with self-attention. In the last two classes, I was talking about self-attention. When you are calculating the attentions, you remember that we defined carry, key, and value vectors. This input sequence was multiplied by carry matrix, key matrix, and value matrices. And having that, we're going to have update tokens. This is input token, and this is updated token. Of course, this Q value, K value, and V value will be determined during the backpropagation in the training processes. So Q means how much each word importance. K is how much importance of each word to other related wordings. V is the total value of each wording. By having this matrix, we're gonna update input embed. Token is by the addition of word embedding and positional encoding. And at each encoder step, this token will be updated. And it will propagate up to final encoder. This is layer 1 encoder. This is layer 2, layer N encoder. So encoder will have multi-layer transformer encoders. And finally, it's going to have output H1, H2 to HT. One important feature of this encoder in the transformer model is that all these X1, X2 to XT are processed in parallel. Carry, key, and value calculation will occur in parallel, and this output H1, H2, HT will be given instantaneously together at the same time. Why? In the previous generative models, such as RNN and LSTM, they are having sequential inputs and output will be in sequential. So what is the disadvantage of previous generative models compared to transformer model is that it takes longer time to process, encoding process. But people are not patient enough. If I am sending a message to OpenAI, yesterday I asked OpenAI to write a poem to describe the colorful the feature of colorful trees in the Gyeryong Mountain, and the OpenAI gave me the poem in a second. So people are not patient enough to wait until a minute or 10 minutes until we give us the response from the OpenAI. So one of the ways to reduce the response time of transform model is doing the parallel processing. This is a clue of future semiconductor and computer architectures. In parallel, X1, X2 to XT, during the propagation through the encoder, each token has to calculate carry, key, and value vectors. And they have to do it simultaneously. Simultaneously means the time jitter between x1 to xt could be less than a nanosecond, something like that. So only way to do that is each GPU cores may have many number of cores so that they can do this calculation in parallel in time. So clock distribution is also very important to make synchronous parallel computing. Now, let's move on to the decoder architecture. This is encoder. Decoder has one T dash. Decoder output sequence number T dash may not be the same as the input sequence number. Also, it has word embedding plus positional encoding. It's gonna go to decoder with masked self-attention decoder with cross attention This is the whole architecture of transformer model. Now, encoder output matrix sequence could be represented by H matrix, and encoder has key and V value. That is supplied to decoder. Decoder has certain input and carry. Please remember that in encoder self-attention, they are calculating carry, K, and V. Each token vector is multiplied by carry matrix to have carry and key and value. I don't want to spend whole classes to revisit this carry, key, and value. But at the final stage, output is H, and each output has carry and V value. That it is going to be connected to decoder. Later on, I'm going to tell you about that. That is called cross attention. So cross attention is a kind of matrix formalism to make a connection between encoder and decoder. And cross attention means how much each wording at the output sequence has importance to the output of encoder. Another important feature of the decoder is masked self-attention. It is a little bit difficult to understand. If you have Y1 output that is going to go back to the input of decoder, and it will generate Y2, and Y2 is supplied to input. So decoder output is sequential process. Encoder process is parallel process, and decoder process is sequential process. If this is Korean language and output is English language, I'm a student, and 나는 학생입니다. And first one is generated, then it is becoming the input of encoder, decoder, and then it's gonna generate the second wording. 나는 학생. And 학생 is coming back again here, and we're gonna generate Y3입니다. So in masked self-attention, they are not considering what the future wording is. Only consider previous wording sequences, Y1, Y2, and Y3. This is overview of decoder architecture. One, I think, very unique architecture of decoder number one is positional cross attention. Second is positional encoding. Third one is masked self-attention. In this class today, one by one, I'm gonna introduce you to this 1, 2, 3. I know that it takes long time to understand all these architectures. Probably you may need papers, and you may need a practice for a month or more. But at least these figures and my explanation at this moment will be very helpful to you to start. Initially, it is very difficult to understand, especially if you are very familiar with semiconductor transistors and circuit theories and logic functions. This is completely different, not easy to understand. The rule is this architecture works very well. We are not clearly it is not easily to understand. Now, I'd like to talk about cross attention. I'm a little bit afraid to tell you that this is not easy to give a lecture and easy to understand, but next one and a week after next one, gradually it is going to be tougher and tougher. In the decoder, input is previous token, G. Input will propagate as a form of token. At the decoder, we have carry. So this is the token, decoder token. Eventually, this token will be converted to output sequence Y1, Y2 to YT. I'm a boy, I'm studying at KAIST. But while we are going through the multiple decoder with cross attention, at this step, decoder token input is represented by G vector. Initially, this input token was converted to update token by having word embedding and positional encoding. And this is the carry of decoder. Of course, this Q value will be updated during the backpropagation. This one is encoder output. You remember that encoder output is described by Y1, H1, H2 to HT sequence. And this is key value, key of encoder. And this key value is also updated during the backpropagation. So by multiplying by the decoder carry multiplied by encoder key, we're gonna generate a new number. That is the real number. The size of that sequence is T by T. And by having softmax, we're gonna have probability distribution. Then it is multiplied by decoder value. We can have update the token. So somehow this carry is obtained from the decoder and the key is obtained from the encoder. By multiplying those two, we can update the token. And at the final stage, it's gonna give you the probability distribution of your best wording sequence Y1, Y2 to YT. There is a paper to introduce transformer model, and the name of the paper is Attention is All You Need. Why is that? This attention mechanism is most distinctive, different from the previous large language model. And the self-attention means, in a sentence, how much relationship, importance of relation between them, that is represented by a carry, key, and value matrices. But in cross-attention value, Q, K, V means how much relationship it has between the output sequence 2 with decoder sequence, encoder sequences. So this Q matrix, K matrix, and H matrix actually make a connection between encoder to decoder. Somehow this is a magic about OpenAI. OpenAI is the representative transform model which gives the best sentence as if he is a human. Sometimes he write, sometimes Hyuna maybe you submit a paper to EPPS. Did you check the grammar using OpenAI, or you totally write your own English? Both methods, yeah. But sometimes OpenAI English is too good, to me. This is overall picture of a transformer architecture. Now, I would like to move on to the positional encoding. Very unique feature of decoder in transformer model is I said that number one is cross attention, number two is positional encoding, and number three is word embedding. So step by step, I would like to introduce that. And overall, in the transform model, most important feature is number one, self-attention and cross-attention. Number two, parallel encoding, serial decoding. In the future, I'm working in Microsoft or OpenAI CTO as an OpenAI CTO. I would like to give a task to a team to convert this serial output of decoder to parallel output. Instantaneously, they make a translation from Korean to English. I think some people are doing that, because that is how we can generate texts or images in a very short time. So what I'm saying is parallelism is also very important feature of future transform model. And the last one is synchronization of parallel computing. How can we do that? That's the way to change the computer architecture, semiconductor, as well as transform model architecture. Now, let's focus on the positional encoding. So, as I said, input has 512 bit coding. There might be many different ways of word embedding. You may have different grouping of each languages, or depending on subject, you may have different categories. And so you can first 10 bit can be used for categorization of each wording or something like that. Another important thing is we add positional information. Positional information means in the 512-bit sequence, you add positional information. From 0 to T. And by having XT plus PT, it's gonna be GT. It's gonna be a token input to this decoder. So numerically, it is added together. The position information is from 1 to T. How are we going to convert all those position information into 512 bit? Probably from 0 to T, linearly, you may have physical position, and you can convert that to 512 bit. 512 bit is huge number. So first sentence position could be 1, 2, up to T, 512 bit to that's a huge number. So you convert position into 512 2-bit sequence, and you add them together. That is becoming positional encoding. I know that Korean language and English language has different sequences. Object, verb, what is that? OSV라고 그러나요? 뭐라 그러죠? 주어를 영어로 뭐라 그래요? SVO. This is English type. Am I right? Korean type is SOV. Am I right? 아버지가 방에 들어가신다. 아버지 가방에 들어가신다. So the space and positions are very, depending on that, very different. Sometimes when you are writing a poem, you break the grammar. Sometimes you put some important wording in. So position is very important feature of a language model. So transformer model is much better than previous models. Second thing is the positional encoding. Of course, we need more memory and more computations. Let's assume our this is my imagination. I haven't actually applied this positional encoding method in real programming. But let's assume that our coding function is represented by multiplication of I and multiplication of J. I means position between the word sequence from 1 to T, wording sequence, and J means the position in the encoded bit from in the 512 bit. We want to make an encoder, positional encoder, which contains the position in the sequence 1 to T, and also we want to make a distinctive differences between, in each token we have 512 bit, and here position in the bit. And if we multiply that, this is the maximum position, we can have this kind of map. This is the 0 position. So my imagination is, in terms of index, we have two axes. One is sequence position, second is bit position of token. By multiplying that, we can have 2D maps. And that is actually added to initial previous token, and it is updated. Another way of doing that is Fij may be sine I sine j. I don't know how to explain that. Sometimes sine function is more likely nonlinear function. Sometimes nonlinear or exponential function may work better compared to linear. I think depending on each companies of transformer model, a large language model, they may have different recipes. And they may not know, but some of them works very well for certain languages. Some of them may be very good for certain languages. But my instinct is saying that anyway, we have to convert this position information and bit position information into two-dimensional space. And one easiest way is the linear function. Second one is the nonlinear function, such as sine and cosine function. And I know that OpenAI is using sine and cosine function. They are not explaining why I do that, but my impression is that nonlinear function may be a good choice. Now, let's move on to the masked self-attention. It is a little bit more difficult to explain, but I may try my best. Let's assume that output sequence y1 to yt is I am a student at KAIST attending Generative AI class. As I mentioned before, first decoder output y1 will be this one. That is going to be input of the encoder, and that will be converted to token by having word embedding and positional encoding. And then we're going to generate y2. And then y1 and y2 will be the input of the decoder, and going through this word embedding and positional encoding, and it's going to go through this self-attention, and finally it may go through the cross-attention, and we're going to generate y3. And this may be y4, y5, y6, y7, y8, y9, y10. At each decoding process, it generates y2, y3, which has best relationship with the encoded output H1 to HT. That relationship between encoded word and input wording is controlled by cross-attention. That is connection between decoder and encoder. Now, when they are producing, decoder is producing y4, they don't know anything about y5, y6 to y10. This is future. This is past. When decoder is producing the outcome sequentially, they have to look at only the past. But human being, we are a lot of talking about our future. We are studying here to build up our bright future. But I don't know, somehow transformer model doesn't look at the future. They are producing y4, that is the best probability after y1, y2, and y3. And so they are making attention, self-attention, Q carry V, they are only referencing the past. Past carry Q, K, and V. they are neglecting, they are making it zeros of all the future key Q carry K and value. That is being called as masked self-attention. Here in the encoder, all the input is going through in parallel. They are processing self-attention without any masking. But at the encoder, they are producing the future words. They are only doing the self-attention, and they are calculating attention only. They care about carry, key, and value of previous sequences. So I think there might be some secrets why OpenAI is using transformer model and they have this kind of masked self-attention. Probably when they are developing new transform model of paralleling output, they may have to solve how to deal with future and past. Now, this is the, I would like to close up the classes about the transformer model. Yes, for the last 3 classes, I was talking about the transformer model. This is, at this moment, very promising and generative model for sequential input and sequential output. And it has encoder and decoder architectures. Most important algorithm embedded in this architecture, number 1 is self-attention, number 1 is cross-attention, number 3 is positional encoding, and number 4 is mask self-attention. And now, right now, I was trying to explain the basic architecture of transform model in a case when we have an input sequence of wording and output sequence is wording text. But what I can imagine is that this input sequence could be images and output sequence could be a text. You can input the whole movie and output could be summarized of the whole story of the movie. Or if you can put your novel and output could be the sequence of images so that kind of preliminary movie and sounds. So once again, transformer model has encoder with self-attention and plus positional encoding. We have decoder with cross-attention and output of encoder is connected to a decoder using the cross-attention. So we're going to have input sequence x1 to xt. Output sequence could be y1 to yt. This input could be text, image, or sound. Output may be also text, image, and sound. Many different combinations. At some point in the future, text and image may be simultaneously input together. Right now, input is text and output is text. Input is text, output is image. But there might be 9 different ways of text input, image input, and text, image, sound output. But at some point in the future, all 3, text, image, and sound may be input. Output will be the text, image, and sound. Then we're going to put a movie, and they will update a new different type of movie. Maybe different character, different sound. Maybe we can make many variations of movie. And when sound is become an input, we have sound sequences in time domain. That each step we can convert the sound as by doing the Fourier transform, we can convert that to image file. And image or text, we may have many different ways to convert real sound to the digital input. That is, word embedding can be replaced by sound embedding or image embedding. Of course, data size is much bigger than the text. So 512 bit may not be enough. The size of the token may be million vector size or something like that. If you have, if this could be also the sequence of images. Each sequence may be converted to picture encoding. It could be n-dimensional vectors. Image has many information, so one-dimensional vector may not be enough. It may have multi-dimensional vector, 2D or n-dimensional vectors. So picture embedding, sound embedding probably may be very important. In the picture also and sound also, we have to think about spatial information. Sound, picture here or picture there or time sequence, we may have to create new way of picture encoding and positional encoding. It could be n-dimensional vectors. Of course, compared to text and wording, image has more depth of information, means more memory size and data size. I think this is my estimation of 10 years of evolution of semiconductor, AI algorithm, and supercomputer. That's what I believe. If this is what you help to design your future, and 10 years later, if this is true, just give me an email. Oh, you're right. You did a good job. Okay, are you going to do that? Thank you. This is the end of my class today. And Wednesday, I'm going to go about this picture, how to create a picture. Here, output could be image, and I'm going to introduce several types of generative AI which can produce the images. Thank you for your kind of attention. Thank you.